Take a piece of metal. Any metal will do. Now shine light on it. Nothing unusual happens. Yes. The metal reflects the light. Perhaps it warms slightly, but this is expected. This is ordinary. But look closer. Look at what you cannot see with your eyes alone. Inside that metal, something remarkable is happening. Electrons, those tiny particles that carry electric charge, are absorbing the light. And then, if the light has just the right properties, something extraordinary occurs. The electrons jump out of the metal entirely. They escape, they fly free into the space around them. This is real. This happens. We can measure it. We can capture these electrons, count them, study their energy. This phenomenon is called the photoelectric effect, and I must tell you, when we examine it carefully, when we ask the simple question of why it happens the way it does, we discover something deeply strange about light itself, something that will force us to reconsider what we think we know about the nature of reality. Let me guide you through this mystery. We will take it slowly, step by step, using only simple logic and careful observation. By the end, you will understand something profound. That light, which seems so continuous, so smooth, so wave-like as it travels through space, is actually made of tiny, discrete packages of energy, particles of light, and this discovery opens a door to an entirely new understanding of how the universe works at its smallest scales. First, let us be clear about what we observe when light strikes metal. Imagine a clean surface of metal in a vacuum chamber, connected to instruments that can detect electric current. When we shine light on this metal, we can measure electrons leaving the surface. These electrons create a small electric current that our instruments can detect. This is the photoelectric effect. Now let us think like scientists. Let us ask, what determines whether electrons will be ejected? What controls how many escape? What controls how fast they move once they are free? Before we answer these questions, let me tell you what everyone believed about light at the time this mystery was being studied. The prevailing view was that light is a wave, like ripples on water, like sound moving through air. Light was understood to be a wave moving through space. This wave theory of light was tremendously successful. It explained interference patterns, diffraction, the colors of the rainbow. It was beautiful mathematics, confirmed by countless experiments. According to wave theory, the energy carried by light depends on its intensity, its brightness. A brighter light carries more energy. This makes intuitive sense, does it not? A bright lamp delivers more energy to your skin than a dim one. So naturally, scientists expected that when you shine brighter light on metal, the electrons should absorb more energy and therefore fly out with greater speed. But this is not what happens. Let me tell you what actually happens, because this is where the mystery deepens. When you shine some red light on certain metals, nothing happens. No electrons escape, no current flows. You can make the red light as bright as you wish. You can increase its intensity 1,000-fold, 10,000-fold, and still nothing. Not a single electron emerges. But now take blue light, even very dim blue light, even just the faintest whisper of blue light. And immediately electrons begin to fly out of the metal. This is astonishing. The dim blue light, which carries far less total energy than the bright red light, succeeds where the bright red light fails. How can this be? And there is more. When we measure the energy of the electrons that escape, how fast they are moving, we find that it depends not on how bright the light is, but on its color. Blue light produces faster electrons than red light, violet light even faster still. But making the light brighter does not make the electrons faster. It only makes more of them escape. According to wave theory, this makes no sense. If light is a wave, and a wave's energy depends on its intensity, then bright red light should eventually give electrons enough energy to escape, but it does not, never. You can wait as. Long as you wish, shine red light as bright as the sun, and from certain metals no electrons will emerge. There is one more crucial observation. For each type of metal, there exists a specific threshold. Below a certain color, below a certain frequency of light, nothing happens. Above that frequency, electrons escape immediately. This threshold has nothing to do with brightness. It depends only on the frequency, which is another way of saying the color of the light. We must pause here and think carefully. What is reality trying to tell us? Let me propose to you a different way of understanding light. It is simple but radical. What if light is not a continuous wave, but rather consists of tiny, indivisible packets of energy? What if light arrives at the metal surface not as a smooth, continuous flow, but as individual particles, little bullets of energy, if you will? Let us call each packet a quantum of light. Today we call them photons, but the essential idea is this: light comes in discrete pieces. Each piece carries a specific amount of energy, and this energy depends on the frequency of the light. Here is the key relationship. The energy of each quantum is proportional to its frequency. Blue light has higher frequency than red light, and therefore each quantum of blue light carries more energy than each quantum of red light. Let us write this simply. If we call the frequency of light F, then the energy E of each quantum is given by E equals hf. The symbol h is simply a constant, a number that nature provides. We call it Planck's constant after Max Planck, who first introduced the quantum idea for different reasons, but the relationship is what matters. Energy equals this constant times the frequency. Now let us return to the metal and think about what happens when these quanta of light strike its surface. Inside the metal, electrons are bound. They are held in place by electric forces, attracted to the positive charges in the metal's atomic structure. To escape, an electron must receive enough energy to overcome this binding. Think of it like this. Imagine a ball resting in a bowl. To get the ball out of the bowl, you must give it enough energy to roll up and over the edge. If you tap it gently, it rolls partway up and falls back. Only a sufficiently strong push will free it. The electron is like this ball. The binding force is like the bowl, and the quantum of light is like the push. When a quantum of red light strikes an electron, it delivers a specific amount of energy determined by the frequency of red light. If this energy is less than what is needed to free the electron cannot escape. It does not matter how many red quanta arrive. Each one individually lacks sufficient energy. They do not add up in a useful way because the interaction between a single quantum and a single electron is an all or nothing event. One quantum interacts with one electron, but a quantum of blue light has higher frequency and therefore higher energy if this energy exceeds the threshold needed to free the electron. The electron absorbs the quantum, gains its energy, and escapes. Any leftover energy becomes the kinetic energy of the electron, the energy of its motion. Do you see? This explains everything. Why does dim blue light work while bright red light fails? Because each individual blue quantum carries enough energy to free an electron, while each red quantum does not. The brightness only determines how many quanta arrive, not how much energy each one carries. Why do electrons from blue light move faster than electrons from red light? Because blue quanta have more energy. After an electron uses some energy to escape, whatever remains becomes its speed. Higher frequency means more leftover energy, which means faster motion. Why is there a threshold frequency for each metal? Because each metal has a specific binding energy, a specific minimum energy required to free an electron. Light must have high enough frequency that each quantum carries at least this much energy. Below this frequency, no individual quantum can do the job, and so no electrons escape, regardless of intensity. All of these strange observations, which make no sense if light is a wave, suddenly become perfectly logical when we understand that light consists of quanta. The photoelectric effect is not complicated. It is beautifully simple, but it reveals something profound. Light has a dual nature. In some situations, it behaves like a wave spreading out, creating interference patterns. In other situations, particularly when interacting with matter, it behaves like a stream of particles, each carrying a discrete packet of energy. Let us consider what this means more deeply. For centuries, we argued about whether light is a wave or a particle. Newton believed it was particles. Later experiments with interference seemed to prove it was waves. Now we find that it is both, or perhaps neither. It is something that defies our everyday intuition, something that exhibits both wave-like and particle-like properties, depending on how we observe it. This is our first glimpse into quantum reality. The photoelectric effect opened a door to a realm where nature does not behave according to the continuous deterministic rules of classical physics. Energy comes in chunks. Interactions happen in discrete events. An electron absorbs one quantum, or it does not. There is no in between. When you flip a light switch and the room illuminates, you are not experiencing a smooth flow of wave energy. You are being bombarded by trillions upon trillions of tiny particles of light, each carrying a precise amount of energy determined by the frequency of the light source. Your eye cannot detect individual photons. There are two. Many arriving too rapidly, but they are there nonetheless. Every beam of sunlight that warms your face is made of these quanta. Every star in the night sky sends them across vast distances of space. The light from your phone screen, the glow of a candle, the flash of lightning, all of it consists of photons, these fundamental particles of light. But there is something else I want you to understand, something deeper. The photoelectric effect tells us that energy at the smallest scales is quantized. It comes in discrete units. This is not just true for light. It turns out to be a fundamental principle of nature. Electrons in atoms can only occupy certain specific energy levels. They cannot exist in between. When an electron jumps from one level to another, it must absorb or emit a quantum of energy, usually in the form of light. This is why atoms emit light at specific colors. This is why each element has a unique spectral signature. The energy levels are quantized, and the differences between levels determine the frequency, and therefore the energy of the photons emitted or absorbed. Think about what this means. At the foundation of reality, there is a kind of graniness. Nature is not infinitely smooth. There are smallest units, fundamental quanta, beneath which you cannot subdivide further. The universe at its core is digital in a sense, made of discrete bits of energy and action. This insight changed everything. It led to quantum mechanics, an entirely new framework for understanding atoms, molecules, light, and matter. It explained the structure of the periodic table. It led to technologies like lasers, semiconductors, solar cells, LED lights, and all of modern electronics. Your phone, your computer, the screen you might be watching this on, all of these depend on quantum mechanics, which began with this simple observation: light comes in quanta. I want to acknowledge something honestly. This quantum nature of light is strange. It feels wrong to our intuition because our everyday experience is with large objects and vast numbers of photons. We never see individual quanta. We see only the averaged collective behavior of countless particles, which appears smooth and wave-like. But when we design experiments to look closely, to examine individual interactions between light and matter, the quantum nature reveals itself. The photoelectric effect is one such window. It is elegant because the prediction is clear and the observation is unambiguous. Either an electron escapes or it does not. Either the quantum has enough energy or it does not. There is no room for confusion here, no need for complicated mathematics to see the truth. The simplicity is what makes it so powerful. A child could understand the basic logic. Light is made of particles. Each particle has energy based on its color, and if a particle has enough energy, it can knock an electron free. Let me bring you back to where we started, a simple piece of metal, light shining on its surface, electrons escaping into the surrounding space. Such a modest phenomenon, and yet it revealed one of the deepest truths about the nature of light and energy. It showed us that reality, when examined closely enough, does not obey the smooth, continuous rules we imagined. It is granular, quantum, fundamentally discrete. This is not abstract philosophy. This is the way the universe actually works. Every interaction between light and matter, everywhere in the cosmos, follows these rules. The photoelectric effect happens constantly in solar panels converting sunlight to electricity, in your eye when photons strike the retina, in photosynthesis where plants capture light energy, in the sensors of cameras. Understanding this does not diminish the beauty of light. If anything, it deepens it. Light is not just a wave or a particle. It is something richer, something that transcends our simple categories. It is quantum, and in being quantum, it reminds us that nature is more subtle, more surprising, more wonderful than we ever expected. When I first understood the photoelectric effect clearly, when I realized that thinking of light as quanta resolved all the paradoxes, I felt a sense of satisfaction that is difficult to describe, not because I had solved a puzzle, but because reality had revealed something true, something that was always there, waiting to be understood. This is the joy of science, not inventing explanations, but discovering what actually is, not imposing our ideas on nature, but listening carefully to what nature tells us through observation and experiment. The photoelectric effect spoke clearly. It told us that light is quantized. All we had to do was listen. I hope you can feel some of that wonder now. I hope you understand that this is not about memorizing facts or formulas. It is about seeing the universe more clearly. It is about recognizing that beneath the ordinary surface of everyday experience, there is a deeper reality, strange, beautiful, and precisely describable, the universe is quantum. Light is made of particles. Energy comes in discrete packets. These are not opinions or theories that might change tomorrow. They are fundamental truths about reality, confirmed by every experiment we have ever done. And here is the most beautiful part. You do not need to be a physicist to appreciate this. You only need to think carefully, to follow the logic, to let the observations guide you. The universe is comprehensible. It can be understood, not all at once, not without effort, but step by step, piece by piece, the picture becomes clear. So the next time you see light sunlight streaming through a window, a street lamp glowing in the darkness, the beam from a flashlight, remember what you now know. You are seeing countless photons, each one a quantum of energy, each one carrying information about its frequency, all of them together creating the phenomenon we call light. And remember that understanding this took careful observation, clear thinking, and the courage to abandon old ideas when they no longer fit reality. This is how we learn what is true. This is how we come to understand the universe. The photoelectric effect is simple, but its implications are profound. It opened the door to quantum mechanics and changed our understanding of reality forever. And it all began with a simple question: why do electrons jump out of metal when light shines on it? Now you know the answer, and you understand a little more about the true nature of light, energy, and the quantum universe we inhabit.